Hi everyone, welcome back. This is lesson 7.1, exponential functions, growth and decay. Your objective for today, by the end of this lesson, you'll be able to write and evaluate exponential expressions to model growth and decay situations. Your vocabulary for today is exponential function, base, asymptote, exponential growth, and exponential decay. Here's an example I'd like you to consider. It says Moore's law, a rule used in the computer industry, states that the number of transistors per integrated circuit, the processing power, doubles every year. Beginning in the early days of integrated circuits, the growth in capacity may be approximated by this table. So notice your X's, which is time, your year, 1965, 66, 67, 68, 69, 70, 71, is a constant change by 1. And notice that the transistors is changing by a multiple of 2. 60 times 2 is 120, 120 times 2, 240, and so on. So you can see that there's a constant rate of change, and this time instead of being added, it's actually multiplied. Growth that doubles every year can be modeled by using a function with a variable as an exponent. This function is known as an exponential function. The parent exponential function is f of x equals b to the x power, where the base b is a constant and the exponent x is the independent variable. So this is different from what we've been doing before. So far we've had exponents and we've also had variables, but we've never had our exponent be the variable. And in a growth function, you're going to see that b is going to be greater than 0 and b will never equal 1, because if you think about it, 1 to any power is still going to be 1. 1 to the first power is 1, 1 to the second power 1, 1 to the third power is still 1. So b will never be equal to 1. Okay, so let's take a look at the graph of the parent function. F of x equals 2 to the x power is the parent function. And so I just want to set it up for you so you can actually see it. When we set up a table to solve this, we say when x is 0, 2 to the 0 power is 1. So our first point is going to be 0, 1. Now think about it. 2 to the first power is 2. So there's our second point. 2 to the second power, that's 2 times 2 is 4. So there's our third point. To the third power, so that's 2 times 2 times 2, that's 8. So there's our third point. So now let's go to the negative numbers. When x is negative 1, remember that that negative doesn't really mean negative when we're talking about exponents. It means to take the reciprocal. So when 2 to the negative 1 power is actually 1/2, so there's our point, and 2 to the negative 2 power is actually 1/4. So the graph of the parent function of f of x equals 2 to the x power is going to look like this. Notice that as the x value decreases, the graph of the function gets closer and closer to the x-axis. So we're talking about right in here. Notice as it gets closer and closer to the x-axis. The function never reaches the x-axis because the value of 2 to the x power cannot be 0. So there's nothing we can multiply 2 to the x power to get 0. So it will get infinitely close to that x but never actually touch it. In this case, the x-axis is an asymptote. An asymptote is a line that a graphed function approaches as the value gets very, very large or very small, but it never will touch that line. A function in the form f of x equals a times b to the x power, with a being larger than 0 and b being larger than 1, is an exponential growth. All right, an exponential growth, which increases as x increases. So you're going to see it do something like what we just saw. It's going to increase, okay, as x increases. When 0 is less than b and b is less than 1, the function is called an exponential decay, all right, function, which decreases as x increases. So that is going to be something that's going to be going more down. So here's two important things to remember. In the function y equals b of x, y is a function of x because the value of y depends on the value of x. And that's not really anything new, but you'll just want to keep that in the back of your mind. And also, as I mentioned before, negative exponents indicate a reciprocal. So notice x to the negative 2 power is actually the same as 1 over x squared. And that may be new to you, may not be, but that's what you need to make sure you remember. And if not, we'll talk about that some more in class. All right, so let's take a look at the first example, graphing exponential functions. The question asks us to tell whether the function shows growth or decay and then to graph the function. So the step one, we want to find the value of the base. Now remember, the base is the part of the problem that is going to be raised to some power. So our base in this case is 3/4. So since the base is less than 1, this is an exponential decay function. So I want to just kind of prove that out to you. If our problem says 3/4 and we're going to raise it to the first power, that would be 3/4. Raised to the second power, 3/4 raised to the second power is actually 9 over 16, 9/16. And then if we raise it to the third power, 3/4 raised to the third power, 3 times 3 times 3 is 27. And 4 times 4 is 16 times 4 is 64. So you can see 3/4 to 9/16 is getting smaller, and 9/16 to 27 over 64 is even smaller. So our function is getting smaller and smaller as our x is getting larger and larger. So next we need to graph this function. You'll be able to do this either on your calculator or by just by hand by using the table of values. The first time I'm going to show you is just using the table of values. So when we put together our table of values with our exponents, we end up with a graph that looks like this. And you can see yet again that as our x's get larger and larger, my function is actually getting smaller and smaller. All right, a second example, tell whether the function shows growth or decay, and then graph. All right, so once again, step one, we want to take a look at the value of the base. Notice this time the value of my base, 1.5, is greater than 1. Okay, so that's going to tell us this is going to be an exponential growth. So this time, if you just put it into your calculator, using your graphing calculator, you can see that in the end it actually looks like it's growing. As the x gets larger, my graph is getting larger also, and that would be an exponential growth. Try one on your own. Go ahead and tell whether the function shows growth or decay and then graph it. All right, so that one shouldn't have been too hard for you. You can see the value of the base is 1.2, and that is greater than 1, so this is going to be an exponential growth function. You can use a table or your calculator. In this case, I'm going to show you the table. Here's the table when you work out your problem, and then the growth is going to look something like this. As you can see, the graph gets larger as my x is getting larger. My x is getting larger, my y is getting larger. All right, you can model growth or decay by a constant percent increase or decrease with the following formula. So you may want to write this formula down and have it in your notes. This is our final amount, our y, and it's dependent on my variable t. All right, and here, this is the initial amount that you start out with, and this is the rate of increase, our r. All right, and so if it's going to be decreasing or increase will depend on whether it's a plus or minus. And my t is going to be the number of time periods. All right, so the final amount is going to be dependent on my time. Time is not dependent on the final amount. So in the formula, the base of the exponential expression 1 plus r is called the growth factor, and similarly 1 minus r is the decay factor. All right, so helpful hint, when X is used on the graphing calculator for the variable t. So when you put in your calculator y equals and then put this function in, you won't put in t, just go ahead and put your variable x and that'll work just fine. Okay, let's take a look at an example. This says Clara invests $5,000 in an account that pays 6.25% interest per year. After how many years will her investment be worth $10,000? So step one, you're going to write a function to model the growth in value of her investment. So here's our function. F of t equals a1 plus r to the t power. So this is the exponential growth function, and we're using the growth function because we want her money to grow from 5,000 to 10,000. All right, so now we need to substitute. So her original investment is going to be the A. So in place of A, I'm going to put her original investment. All right, next we use our exponential growth, which is 1 plus r. So 1 plus r is the rate, and it tells us that our rate is 6.25%. And notice when you change percent to a decimal, you just move your decimal point 2 places over. So it was here, and we just move it 2 places over, and that way you can put your percent in your calculator like that. All right, and then t is going to be our time in years, all right, because we're talking about how many years will her investment will be worth $10,000. So there's all of our substitutions. So now, when you simplify it all, you're going to have f of t equals 5,000 times 1.625 to the t power. And you can just put that into your calculator. Okay, step 2 of this example. Just a side note here, when graphing exponential functions in an appropriate domain, you may need to adjust the range a few times to show the key points of the function. That just means you're going to need to go to your Windows section and adjust on your calculator so you can get the graph to look more usable. So step 3 then, you're going to use your graph to predict when the value of the investment will reach 10,000. And the way you can do that is use the trace feature to find the t value where f of t equals 10,000. And remember, it's the t value for time, but we're going to be calling it x on your calculator. And so we could just use that trace feature until you get to where you see y is equal to close to 10,000. All right, so here's just another picture of that. Use your trace feature to find it, and when you're in the table, you could also find it that way. Another way we'll be able to find it, and I'm going to show you this in class, is you'll be able to find exactly what t equals to make it 10,000. T equals 11.43 is actually the exact amount, and I will show you when we get into class how to do that on your calculator. If you want to figure that out on your own, you can use the solver in the math section to help you solve that. All right, so try this one on your own. Turn your video off and give it a try. So, hope you could figure this one out pretty easily. It says in 1981, the Australian humpback whale population was 350 and increased at a rate of 14% each year since then. Write a function to model population growth. Use a graph to predict when the population will reach 20,000. So the first thing we want to do, step 1, is to write your exponential growth function. Okay, so remember, what is A? A is our beginning amount, and so we're going to substitute A with 350, and our percent increase is going to be 14%. So remember, to change 14% to a decimal, we just have to move your decimal point 2 places over to the left. All right, so now that we have our function set up, we're going to simplify it, and there it is. So now you can put in your calculator y equals 350 times, and use your parentheses, 1.14, close your parentheses, to the raised to the x power. All right, so once you've got that in your calculator, you can hit your graph and trace, and then you will be able to just trace on up until you find that the y is close to 20,000. So here our y is 20,000. It's not exactly, but we can see it's going to be close to year 31. All right, so it will take about 31 years for the population to reach 20,000. All right, and one more last example. A city population which was initially 15,500 has been dropping 3% a year. Write an exponential function and graph the function. Use the graph to predict when the population will drop below 8,000. All right, so once again, the very first thing we want to do is write an exponential decay function because we're dropping now. Okay, so now it's going to be using a minus sign in here. Okay. So again, we're going to substitute. Remember, A is our initial amount, which is 15,500, and we're dropping by 3%. So make sure you remember you have to change your percent to 0.03. Move your decimal point over. All right, and now simplify your equation, and then just type it into your calculator, y equals. And when you do that, you can then see a graph and then use your trace to trace down to where we get to the y is going to be close to 8,000, and here we see in 22 years. All right, so it will take about 22 years for the population to fall below 8,000 if it continues on this trend. All right, one for you to try on your own. A motor scooter purchased for $1,000 depreciates at an annual rate of 15%. Write an exponential function and graph the function. Use the graph to predict when the value will fall below $100. So go ahead and turn the video off and give this one a try on your own. Okay, so the very first thing you want to do is write your exponential decay function, because notice that it says when it's falling, it's going below. Okay, we're losing. All right, and so we're going to use the minus. Remember, our initial amount is our A, so that's going to be 1,000, and then we're going to multiply times 1 minus 0.15 to the t power. So go ahead and simplify that. Then you get it into your calculator. You should say something like this, and when we want it to go below 100, you can see that eventually at 14.2 it goes below. So it'll take about 14.2 years for the value to fall below $100 if it continues this trend. All right, so that's the end of this video, and I just want you to see how important these exponential growths can be to you. And this is a real life example. If you right now at 15, 16, 17 save $1,000 a year and put it in an IRA for $1,000, and then when you turn 20 you stop saving, don't do anything else, you just stop your savings and leave that $4,000, $5,000 in your account. If you don't do anything, by the time you turn 65, you will have made $107,000 on that money. So you didn't have to do anything. You just, when you were working in 15, 16, 17, you put that money aside. It's going to increase quite a bit. You can see the exponential growth of that. Now, you still make quite a bit of money if you start and do the exact same thing when you're 25 years old. You start saving for 4 years, 4 or 5 years, put $1,000 in each year. By the time you're 65, that $4,000, $5,000 will have increased all the way to $54,000. That's a pretty nice increase. But if you start right now, you're going to double your money at $107,000 when you're 65. So might be a good time for you to start saving and take advantage of that exponential growth. Okay, that's the end of the lesson for today. Hope you have a great day, and I will see you in class. Bye.